Hello everyone. Hope you are doing very well. So today we are going to discuss some JEE PYQs that has been there in the previous JEE examinations. So let's start today's topic, that is NCERT chapter 4 D and F block elements JEE PYQs. This is disclaimer. So let's begin with our first question. This is a JEE PYQ and this is covering the NCERT section 4.3.9. The question is that the magnetic moment of a transition metal compound has been calculated to be 3.87 Bohr magneton. The metal ion is. So we have given the magnetic moment of a transition metal compound whose value is 3.87 Bohr magneton. You have to identify the metal ion which is associated with this magnetic moment from the given options. The options are chromium 2 positive, manganese 2 positive, V2 positive, vanadium 2 positive, or titanium 2 positive. So you have given some time. Try to solve this and then we will conclude to its correct answer. Let's see. So for this given question, the correct answer is option third, that is vanadium 2 positive. Let's see how. So for calculating the magnetic moment, the formula which we have studied is given by mu is equals to under root nn plus 2 Bohr magneton. Bohr magneton here is the unit for calculating the Bohr magnetic moment. Mu is representing the magnetic moment. N is representing the number of unpaired electrons present in the element. So N is number of unpaired electrons. Now calculating the magnetic moment for each option. So basically you have the formula for the magnetic moment. You have the value for the magnetic moment. You just have to put this value and this formula for every option. So let's see. Let's see for the first one, that is chromium 2 positive. Now the chromium atomic number is 24, right? So you have to write the configuration. So configuration of electronic configuration of chromium will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. Every orbital is filled other than 3d5 and 4s1, right? So we consider these two for calculating the number of unpaired electrons. So electronic configuration of chromium 2 positive, because we have given the option as chromium 2 positive. So 2 positive means 2 electrons will be removed from its outermost shell, that is from 1 from 4s1 and 1 from 3d5. So the chromium 2 positive configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6, 3d4. D orbital will contain now only 4 number of electrons. That means this configuration can also be written as argon 3d4, 4s0, because other than this 3d4, this stable configuration is of the noble gas argon. So it can be written as argon 3d4, 4s0. From here, the n value, that is the number of unpaired electrons value, is calculated as 4, because d4 means we have 4 unpaired electrons present in the d orbital. We simply now put this in the magnetic moment formula. So mu is equals to 4 multiplied by 4 plus 2 whole under root. So 4 plus 2 is 6, 6 times 4 is 24. So mu will be equals to under root 24, or you can write in decimal places after solving this under root value, which is equals to 4.89 Bohr magneton. Okay. So under root 25 is 5. Under root 24 will be 4.67 something, right? So it is equals to 4.89 Bohr magneton. So the given Bohr magneton value is 3.87, which is lesser than 4.89, which we have calculated for chromium 2 positive. That means this can't be the answer. So let's solve for another option. Now let's solve for manganese 2 positive. Similar steps, the atomic number of manganese you have to identify, you have to know, that is 25. Now, the electronic configuration of manganese you have to write, which is given by 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2. Now, we have to write the configuration for manganese 2 positive. 2 positive means 2 electrons will be removed. That means from this 4s2, 2 electrons will be removed. The remaining configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. You can also write it as argon 3d5, 4s0. Now here the n value, the unpaired electron value is 5, which is d from the d5 orbital. So we put it in the formula of the magnetic moment. So mu will become equals to under root 5, 5 plus 2. 5 plus 2 is 7. 7 times 5 is 35. So mu is equals to under root 35. Now when you write it in the decimal, it will be equals to 5.91 Bohr magneton, because under root 36 is 6. So under root 35 will be 5 point something. So 5.91 Bohr magneton. Now this is also not matching with the given magnetic moment value in the question. So this option can't be the answer. So we have to repeat similar steps for our next option. For the vanadium 2 positive, the atomic number of vanadium is 23. The electronic configuration of vanadium is given by 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. And for vanadium 2 positive, 2 electrons will be removed. Then configuration will become 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, because 2 electrons will remove from this 4s2. So it can also be written as argon 3d3, 4s0, right? So from here, the number of unpaired electrons is from the d3 orbital, that is 3. N equals to 3. Now we put this n equals to 3 in our magnetic moment formula. So mu will become equals to under root 3 times 3 plus 2. 3 plus 2 is 5. 5 times 3 is 15. So mu is equals to under root 15, which is equals to 3.87 Bohr magneton. Because under root 16 is 4. So under root 15 is 3.87 Bohr magneton. Now this value and the given magnetic moment value in the question is matching. So vanadium 2 positive will become our correct answer. Similarly, the fourth option, let's calculate for this too, because maybe this also can have same magnetic moment, right? So for just the surety, the titanium 2 positive, so titanium atomic number will be 22. Its electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. Okay. It can also be written for the titanium 2 positive. So 2 electrons will be removed from 4s2. So electronic configuration will become this. 3d2 will be there in the outermost orbital. So it can also be written as argon 3d2, 4s0. From here, the n value is coming out as 2 from the d2 orbital. So when you put it in the magnetic moment formula, it will become under root 2 times 2 plus 2. 2 plus 2 is 4. 4 times 2 is 8. So mu is equals to under root 8 or 2.82 Bohr magnet. 2.82 and 3.87 are very, very different. So this can't be the correct answer, right? Because the magnetic moment value is not matching. Hence, our correct answer will be the vanadium 2 positive, because vanadium 2 positive magnetic moment is matching with the magnetic moment value given in our question. Hence, the metal ion with a magnetic moment of 3.87 Bohr magneton is vanadium in the +2 oxidation state. Okay, let's move to our next question. So, this is a JEE PYQ which is covering the NCERT section 4.4. The question is, correct order of basicity of the oxides of vanadium is. So we have given the order of the vanadium oxides. You have to select the correct order for basicity of oxides of vanadium. The options are V2O3 highest, having highest basicity, then V2O4, then V2O5. V2O3 having highest basicity, then V2O5, then V2O4. V2O5 having highest basicity, then V2O4, then V2O3. Or V2O4 is having highest basicity, then V2O3, then V2O5. So choose the correct order of basicity of oxides of vanadium. you can simply calculate. Here only one thing can be vary, that is oxidation state. Yeah, right. So you can calculate that and then you can conclude to the basicity. So you have given some time, try to solve this, then we will see the correct answer. See, for this given question, the correct answer is option first, that is V2O3 is having the highest basicity, then V2O4, and then V2O5. So the basicity of metal oxides generally decreases as the oxidation state of metal increases. So this is the concept on which we are going to answer this question. That is for oxidation state. You have to calculate the oxidation state for each oxides given, and then you have to apply this concept that generally as the oxidation state increases, the basicity of metal will decrease. So step 1 includes the determining of oxidation state of vanadium in the each oxide. So V2O3, in the V2O3, let the oxidation state of vanadium be X. So for calculation of the oxidation state, so it will become 2X because 2 vanadium plus 3 times the oxidation state minus 2. So 2X plus 3 times minus 2 become equals to 0. That means 2X minus 6 equals to 0. From here, 2X equals to 6 and X equals to plus 3. So the vanadium oxidation state from here is coming equals to plus 3. So in the V2O3, vanadium is in plus 3 oxidation state. Similarly, for the V2O4, let the oxidation state of vanadium be Y. So oxidation state will be 2Y plus 4 times minus 2 equals to 0. Equals to 0 we are putting because this is a neutral molecule. It doesn't have any charge. If it is having any charge, overall charge over this molecule, that charge will be going to put at the place of the 0. Okay. So 2y plus 4 times minus 2 will be minus 8. So 2y minus 8 equals to 0. From here 2y equals to 8. And from that y equals to plus 4 because 2 times 4 is 8. So the oxidation state of vanadium is coming out as equals to plus 4. So in the V2O4, vanadium is in plus 4 oxidation state. Now V2O5. So for V2O5, let oxidation state of VB, vanadium be Z. So 2Z plus 5 times minus 2 equals to 0. 2Z minus 10 equals to 0. This implies 2Z equals to 10 because this 10 will go here. And from here, Z will become equals to plus 5. 2 times 5 is 10. So in the vanadium pentoxide, V2O5, vanadium is in plus 5 oxidation state. So let's see the reasoning that lower oxidation state, that means in the lower oxidation states, the metals are more electron rich, right? Because it is having a lower oxidation state. That means either plus 1 or plus 2. That means it has loosened its lower number of lower number of electrons. That means it is more electron rich compared to the oxides having higher oxidation state, right? So in the lower oxidation state, the metal are more electron rich and basic because it is going to act as Lewis base or Bronsted-Lowry base, which based on the concept of electron donating or accepting, right? So it is going to form more ionic bond with the oxygen, that is vanadium. So vanadium is going to form more ionic bond with the oxygen, and metal is having more electron rich when the oxidation state is lower because it has loosened its lesser number of electrons compared to the metal in the higher oxidation state, and it is going to act as a base, that is Lewis base or Bronsted-Lowry base based on the concept of electron donating or accepting. Now the other thing is higher oxidation state. So in higher oxidation state, the metal are more electron deficient because it is having higher oxidation state means higher positive charge. That means it has loosened its high number of electrons comparatively, and the metal is going to be acidic. That means it is going to act as Lewis acid or Bronsted-Lowry acid. That means it is going to form more covalent bonds with the oxygen by sharing of electrons. So the step 2, after the calculation and the understanding of oxidation state of the metal, step 2 includes the apply the rule to the vanadium oxides. So based on the general rule, V2O3, in which the vanadium is in +3 oxidation state, this has lowest oxidation state among the given oxides of vanadium. So it will be most basic. V2O4 is in +4, vanadium oxidation state is +4. So this has intermediate oxidation state from the given oxides. So it will have intermediate basicity. So it is generally considered as amphoteric, which will show both basic and the acidic properties, but less basic than the comparative V2O3. Now V2O5, where vanadium is in +5 state. Now this has highest oxidation state, so it will act as, so it will be least basic, or you can say most acidic, vice versa. Now this V2O5 is known to be amphoteric, but with a predominantly acidic character. So therefore, the correct order of basicity you have to tell, that is most basic to least basic. V2O3 will be most basic. Then V2O4 comes, and least basic will be V2O5. Therefore, the correct answer is, or the correct order will be, highest basicity will be in V2O3, then V2O4, and then V2O5. So option 1 will be going to our correct answer. Let's move to our next question. Now, this is a JEE PYQ, and this is covering the NCERT section 4.4. Question is, highest oxidation state of manganese is exhibited in the Mn2O7. Correct statements about this manganese oxide are, we have given 4 statements. You have to choose the correct statement and then mark the correct answer. So A statement is that manganese is tetrahedrally surrounded by oxygen atoms. Manganese is octahedrally surrounded by oxygen atoms. C statement is that it contains manganese oxygen manganese bridge, Mn2O7, or Mn2O7 contains manganese manganese bond. So you have given 4 these statements. Choose the correct one. So choose the correct answer from the options given below. The options are A and C only, A and D only, B and D only, or B and C only. So you have to choose the pair of the statements that are going to be the correct statement. Okay. So it is directly basis on the properties that we have been studied, or that we have studied on the topic of oxides of like transition elements. Okay. So manganese oxide, what we have studied about that, its oxidation state, its stability, its structure, that you have to focus on. So you have given some time. Try to solve this, analyze this, and then we will going to see the correct answer. Okay, let's see. So for this question, the correct answer is our option first. That is A and C only. A and C statement only. So let's see. This is the structure of Mn2O7. The manganese, oxygen manganese, is the bond by which 2 manganese are joining to each other, and each manganese is attaching with 3 triple bond oxygen bonds, right? Like in tetrahedral manner. Okay, so Mn double bond O, double bond O, double bond O, Mn double bond O, double bond O, and double bond O. And these 2 manganese are joining together by 1 oxygen bond. Now, understanding the structure of manganese oxide include, so Mn2O7 is a compound where the manganese is having +7 oxidation state, which is the highest oxidation state show by manganese, which manganese show. So the structure consists of, this Mn2O7 structure consists of 2 manganese atoms and 7 oxygen atoms. 3 here, 3 here, 1 is here between the two manganese. Okay. Let's analyze each option one by one. The first one, let's analyze the statement A. That is our correct statement basically. So in the Mn2O7, each manganese atom is surrounded by 4 oxygen atoms, right? 3 from there is from like double bonded with oxygen and 1 is single bonded with oxygen. So each manganese in the structure of Mn2O7 is surrounded by 4 oxygen atoms in a tetrahedral arrangement. You can see the diagram. Manganese is having tetrahedral arrangement of oxygen around it. Okay. This is true for one of the manganese centers. So our analysis says that the statement A is correct, which is statement 1 A was that manganese is tetrahedrally surrounded by oxygen. This is correct statement, right? Now let's analyze the B statement, which was our incorrect statement. The B statement says that manganese is octahedrally surrounded by oxygen atom. But we have already said that manganese is tetrahedrally surrounded by oxygen atoms. Statement is correct. So this statement will automatically get cancelled out, right? So analysis says that in manganese oxide, manganese is not surrounded by 6 oxygen atoms. Instead, it is surrounded by 4 in a tetrahedral geometry. You can see this in diagram. So the statement B, which says that manganese is octahedrally surrounded by oxygen atom, is incorrect. Let's analyze the C statement, which says that the structure of Mn2O7 contains manganese oxygen manganese bridge. So this statement is correct. Analysis say that the structure of Mn2O7 includes a bridging oxygen atom. Bridging oxygen atom means one oxygen atom is acting as a bridge between two same atoms to join them together to build the structure. Okay. So in the structure Mn2O7, a bridging oxygen atom is included between the two manganese atoms, which indicating that there is indeed a manganese oxygen manganese linkage. You can see the diagram. There is manganese oxygen manganese bonding. So there is bridging oxygen atom that is acting as a bridge. This bond is acting as a bridge to join between the two manganese atoms. Okay, that means manganese oxygen manganese linkage is present. Hence, this statement C is also going to be the correct statement. Now let's analyze the D statement, which is actually incorrect. Because in the analysis in Mn2O7, there is no direct manganese bond. The manganese atoms are connected through oxygen atoms by forming a bridge. You can see the diagram. We don't have any direct manganese bond. That means this statement D, is going to be the incorrect one. So let's finalize the answer. So the correct statements about the manganese oxide Mn2O7, where the manganese is exhibiting +7 oxidation state, which is the highest manganese oxidation state. So manganese is tetrahedrally surrounded by oxygen atoms. That is the A statement. And it is containing, Mn2O7 is containing MnO-Mn bridge. It is also the correct statement. That is C statement. So thus our correct options, our correct statements are A and C. So option 1 is going to be our correct answer. Okay. Let's move to our next question. This is the JEE PYQ and this is covering the NCERT section 4.3. Question is, a solution of FeCl3 when treated with K4FeCN6 gives a Prussian blue precipitate due to the formation of. So we have given that you have a solution of FeCl3. Okay. Now when you treat this FeCl3 solution with this complex K4FeCN6, you will get a Prussian blue precipitate formation. Okay. Why this happens? due to the formation of what this precipitate you will get of blue color. That you have to tell. So options are KFe2CN whole 6, Fe FeCN whole 6, Fe3 FeCN whole 6 whole twice, or Fe4 FeCN whole 6 whole thrice. So you have given some time, try to solve this, then we will see the correct answer. Okay, let's see. So for this given question, the correct answer is option 4th, that is Fe4 FeCN whole 6 whole thrice. So basically, when the solution of FeCl3 treated with this complex of iron, a Prussian blue precipitate is formed due to the formation of this complex Fe4 FeCN whole 6 whole thrice. Now this is a complex compound which is also known as ferric ferrocyanide. Okay, ferric ferrocyanide. Reaction between the FeCl3 and this complex to get this precipitate can be represented as FeCl3 4 molecules reacts with 3 molecules of this K4 FeCN whole 6 complex, and we will get Fe4 FeCN whole 6 whole thrice ferric ferrocyanide complex plus 12 molecules of potassium chloride. So here from this complex, potassium, which is the cation present at the outside of square bracket, that can be ionized, right? On the basis of complex compounds properties. So this potassium is going to react with the chlorine, and this iron will going to react with the remaining complex pair, okay, and form this another complex compound, ferric ferrocyanide. Thus, the Prussian blue precipitate is a distinctive blue color, which is characteristic of this specific complex compound we are getting. Okay, so the Prussian blue precipitate we are getting is due to the formation of this Fe4 FeCN whole 6 whole thrice, that is ferric ferrocyanide complex compound. Hence, our correct answer is option 4. Okay, let's move to our next question. Now, this is a JEE PYQ, and this is covering the NCERT section 4.4. Question is, when the copper 2 positive ion is treated with potassium iodide, a white precipitate, that is X, appears in the solution. Solution is when treated with sodium thiosulfate, the compound Y is formed. You have to identify the X and Y respectively. Okay, so we have given that the copper ion is when treated with potassium iodide, you will get a white color precipitate, that is X. Now, that X or that solution is when titrated with sodium thiosulfate, you are going to get Y. You have to answer that what is X and Y. Options are that X is Cu2I2, Y is Na2S4O5. X is Cu2I2, Y is Na2S4O6. X is Cu(I2), Y is Na2S4O3, or X is Cu(I2) and Y is Na2S4O6. So you have given some time, try to solve this, try to write the reaction and see what is X and Y. And after this time, we will see that what is going to be our correct answer. Let's see. So for this given question, the correct answer is option 2nd, that X is Cu2I2 and Y is Na2S4O6. So let's go step by step. The step 1 include the reaction of copper 2 plus with the potassium iodide. So when copper in the +2 state, that is copper 2 plus ion, are treated with potassium iodide, a redox reaction will happen. That is, reactant will going to be copper 2 plus, which are going to act as oxidizing agent, and they are in plus 2 oxidation state and tend to gain the electrons. They will gain electrons, so act as oxidizing agent. That means oxidize others and get reduced itself. Other reactant is I negative from potassium iodide, right? So iodide ions are reducing agents. They are in the -1 oxidation state and they will going to lose electrons. That means they are going to act as reducing agents by reducing other and get oxidized itself. Now, what is the redox reaction will happen? In this reaction, the ion of copper oxidized iodide ion to the iodine molecule, and in turn the copper 2 plus itself get reduced to the copper 1, the copper iodide, okay, in the +1 oxidation state. So copper iodide is that product which is going to appear as white precipitate, that is X. The balanced chemical equation, if you want to write out, is 2 copper 2 plus 4 iodide ions. They will give us 2 CuI. So copper 2 plus ion going to reduce this or oxidize. Okay, copper 2 plus ion is going to oxidize this iodine negative, that means iodide ion to iodine molecules, and reduce itself from +2 to +1 and forming copper iodide molecule as a precipitate, as a white color precipitate. What is the observation here? After this reaction happens, that a white color precipitate, that is X, we mentioned in the question, is appearing in the solution, and this white precipitate is nothing but copper iodide molecule. Simultaneously, the iodine which forms in the solution will give the solution a brownish color. Therefore, the X is copper iodide. Now, the step to include the titration of solution with sodium thiosulfate as given in the question. So, the solution now contains a white precipitate, that is copper iodide, and a liberated iodine. Now, when the liberated iodine is treated or titrated with some sodium thiosulfate, that is Na2S2O3. This is a common method for the quantitative determination of oxidizing agents, which is known as iodometric titration. Now, this titration happening between the white precipitate, that is copper iodide, and the liberated iodine in the solution. When this titration happening with sodium thiosulfate, this is a method which is commonly used to quantitatively determine the oxidizing agents, and this method is iodometric titration. The reactant that are going to include, first is the iodine molecule in the aqueous form. So iodine that was liberated in the first step, right? In the first step, from the copper to positive ion, when it oxidizes iodide ion to iodine, from there we get the iodine molecule. Secondly, sodium thiosulfate, that is Na2S2O3. So this titrant thiosulfate ion will going to act as a reducing agent, right? And the redox reaction during the titration that will happen. Now, in this reaction, the iodine we get from the first step is reduced back to the iodide ions from 0 to -1 oxidation state. And the thiosulfate ions, that is S2O3 negative, are going to oxidize to the tetrathionate ions, that is S4O6, after the titration happens. The balanced chemical equation of the second step is iodine molecule react with sodium thiosulfate 2 molecules. We will get sodium iodide and this another formation of compound, that is Na2S4O6, which is going to be our Y, the compound Y. Or in the ionic form, you can write this equation as I2 plus 2S2O3 negative will give us 2I negative plus S4O6 negative. So formation of Y will happen, and the compound Y that is formed during the titration is sodium tetrathionate, that is Na2S4O6 from the sodium thiosulfate and iodine reaction. Therefore, Y will be Na2S4O6, that is sodium tetrathionate. Thus, we can say that our X, that is the first compound in the first step we get is copper iodide in the +1 oxidation state of copper, which is a white precipitate which was formed when the copper 2 positive ion reacts with potassium iodide. And the Y is sodium tetrathionate Na2S4O6, the product that we are getting when the liberated I2 from the first step is titrated with sodium thiosulfate in the second step. So X and Y formulas are these. Okay, let's move on to our next question. So this is a JEE PYQ and this is covering the NCERT section 4.4. The question is, which of the following are the example of double salt? So you have to tell that we have given some, salts A, B, C and D. You have to tell that which are the example of double salt. So the A salt is FeSO4.NH4 whole twice SO4.6H2. B is copper sulfate .4NH34.H2. C is K2SO4.Al2SO4 whole thrice .24H2. And D salt is FeCN whole twice .4KCN. You have to tell that from these salts, which is the example of double salt. Choose the correct answer. Options are A and C only, A and B only, A, B and D only, or B and D only. So focus on the properties of the double salt you have known, and then you can identify the example representing the double salt. You have given some time. Try to analyze this, then we will see the correct answer. Okay, let's see. So for this question, the correct answer is option first, that is A and C only. So a double salt is a type of salt that consists of two different salts, okay, that crystallize together in a fixed ratio. So property of double salt that you have to consider here, that double salt is the type of salt that consists of two different salts, as the name says, double salt. Okay, so it is consisting of two different salts and that is crystallizing together in a fixed ratio. In a fixed ratio, it is existing. It is in a crystalline form. Let's analyze each option one by one. So the first step is the analyzing step. So A is FeSO4.NH4 whole twice SO4.6H2O. Now this compound consists of iron in the +2 oxidation state, so iron sulfate, and ammonium sulfate, 6 molecules of water. Iron is in +2 oxidation state and we have ammonium sulfate. Since it is a combination of two salts, the iron sulfate and ammonium sulfate, it qualifies as a double salt. It is a double salt. Conclusion is that option A is, or this A salt which is given is double salt. Step 2, the B salt. So copper sulfate .4NH3 water. Now this compound consists of two compounds, or you can say two molecules. First is copper +2 sulfate and ammonia. So we have copper sulfate where copper is having +2 oxidation state and the ammonia in one molecule of water. However, this is not a double salt. This B salt is not a double salt because it is a complex salt where ammonia will act as a ligand for the copper ions. Okay, so it is not containing two different salts. It is a complex salt. That means only one salt is present, that is copper sulfate. The another, that is ammonia, is going to act as a ligand for this copper ion present in this salt. Conclusion, that option B is not a double salt. Okay, why? Because it doesn't have two salts in it. One salt is there, copper sulfate. The another salt, that is 4NH3, is going to be act as the ligand for the copper ion, and here copper is going to act as central atom to form the complex. Okay, and this ammonia 4 molecules is going to act as ligand and going to arrange around the copper ion in the complex. So option B, that is this B salt, is not a double salt. Now let's see for the C salt, that is K2SO4.Al2SO4 whole thrice dot 24H2. This compound consists of the potassium sulfate and the aluminium sulfate. Because it is a combination of two salts, it qualifies as a double salt because it has two salts. One is the potassium sulfate and the another is aluminium sulfate. So because it is having two salts, it is going to be act as, or it is going to be a double salt. The conclusion, that C salt is a double salt. Step 4 is for D salt, that is FeCN whole twice dot 4 KCN. Now this compound consists of iron in the +2 oxidation state, cyanide, and potassium cyanide. Here, this is also a complex salt where cyanide ions act as ligands, surround the iron ion, where iron is going to be central matter. Okay, so here also this complex or this salt given in the D is a complex salt where cyanide ion is going to act as ligands, going to arrange themselves around the iron ion, and iron is going to act as central atom or central metal in the complex structure. So conclusion, that option D, that is this D salt, is not a double salt. The final answer is that the correct salts that are the example of double salts are the salt 1 and the salt A and the salt C, because they are the combination of two salts. The other salts present in B and D are complex salts, in which one salt is given and another ligand is given, which is going to act as ligand and going to arrange themselves around the central metal present in those salt. Okay, so our correct answer is going to be A and C. Okay, let's see the question, which is a JEE PYQ, and this is covering the NCERT section 4.4.1. Question is that the number of moles of H positive ions required by the 1 mole of MnO4 negative to oxidize the oxalate ion to CO2 is. You have to tell that what is the number of the moles of H positive ions that you are going to need by 1 mole of MnO4 negative to oxidize this oxalate ion to the carbon dioxide. This oxidation happens, but to oxidize this, what is the number of moles of H positive ions that are going to be needed by this MnO4 negative 1 mole? Options are 4, 8, 5 or 2. So you have to here apply the concept or the reaction that you have been seen of MnO4 negative in different bases, like acidic and the medium and the basic medium we have seen, right? And then you have to conclude to your answer. So you have given some time, try to solve this. Then we will see the correct answer. Okay, let's see. So for this given question, The correct answer is option 2, that is 8. This is going to be the reaction between the MnO4 negative ion and the H positive ions and the oxalate ion. Okay, so 2 MnO4 negative plus 5 C2O4 2 negative plus 16 H positive is going to react to give us 2 Mn2 positive plus 10 molecules of carbon dioxide after the oxidation of oxalate ion plus 8 molecules of water. We have to determine the moles of H positive that is going to required per mole of MnO4 negative to oxidize the oxalate ion to the carbon dioxide. This was the question, right? So from the balanced equation, we have seen 2 moles of MnO4 negative is react with 16 moles of H positive. So 2 moles of MnO4 negative is reacting with 16 moles of H positive to give us 10 molecules of CO2. So for 1 mole of MnO4 negative, we have been asking. So for 1 mole of MnO4 negative, the H positive ion that you are going to require will be, so mole of H positive ion required will be 16 moles of H positive, which you are requiring in the 2 moles of MnO4 negative. So moles of H positive that you are going to require when there is 1 mole of MnO4 negative, that is going to be 8 moles, because 2 moles of MnO4 negative reacting with 16 mole of H positive. So 1 mole of MnO4 negative react with, you have to divide by 2, 8 moles of H positive, because 2 by 2 is 1, 16 by 2 is 8. Okay. So by unity method, we have determined that the number of moles of H positive ions that are required by 1 mole of MnO4 negative to oxidize the oxalate ion to the carbon dioxide is going to be 8. The number of moles is going to be equals to 8. We simply apply the unity method after seeing the balanced equation of the reaction happening between MnO4 negative, oxalate ion and the protons. Hence, our correct answer is option 2, that is 8. Okay. Okay. Thank you so much. That's all for today's chemistry session. Thank you.